All right, thank you for being here. I'm very happy to be able to talk about this topic at PyData. So what I want to talk about today, it's a relatively new method to fit Gaussian processes kind of at scale, so to say. So it's a method that I've been using quite a lot in applications, and I know other PyMC developers are using as well, but we believe this hasn't kind of reached a wider audience because maybe it's too hard or it seems kind of still kind of new to try it out. So my intention with this talk is to give you an overview of how and why this works. And at the beginning might be a little bit confusing, so to say, but that's fine, because the whole point is that we're preparing a lot of material to cover various aspects of this topic. So this material would be more about why does this work, and kind of a glimpse on an example. And we'll be preparing other type of documentation regarding kind of the practicalities. So yeah, please bear with me, and I hope you can find it as useful as we are doing it. So the most important slide is this one, because on this URL, which I can share on Discord later on, there's a fully, and I would say lengthy notebook on which I go through all the details, meaning code and also kind of the math. So you don't need to kind of take notes. I also share the slides. You can also see the slides already if you go there. And so just sit, relax, and take notes on what you don't understand so that you can then go to the notebook and then you could also ask questions. But yeah, I prepare kind of really nice material that hopefully brings this into something tangible. I'm also kind of comparing, well, not comparing, but kind of providing various implementations. So in PyMC, which is a quite friendly, there's a quite friendly API for fitting such models, and also Numpyro, and we do this a little bit by hand. All right. So I'm going to briefly talk about kind of the motivation of some applications, just to go to the straight point and say we are actually using this in industry. I'm going to talk about Gaussian processes, and I'm not going to spend a lot of time here. So kind of this is the sacrifice of the trade-off. I want to, of course, give you an example and provide kind of the problem. The main kind of component of this talk would be about the approximation and why it works. And we are not going to really go up to the last epsilon, but really try to kind of hint the ingredients. And the reason is because the APIs kind of that wrap this function have certain parameters. And if you know what these parameters actually mean, it might help you debug these type of models. And yeah, I'll share some references. I'm going to kind of take it easy, and if I don't cover the material, that's fine, because you have everything online, and you can always reach to me. So about applications, I mean, when people talk about Gaussian processes, they usually talk about the toy example that I'm going to present today, but in reality, it can serve many purposes. So the first kind of case study that where I saw Gaussian processes being a fundamental part of an interesting real model was this blog post by Alex Andorra, and he was trying to model the popularity of presidents in France. So you see kind of the y-axis is between 0 and 1. This is a share of popularity. And he built a very nice model where he was using kind of these Gaussian processes as kind of latent variables for this share kind of variable, and also doing contrafactors. So for example, okay, what if, for example, the unemployment rates would drop to 5%? What would that actually mean in terms of popularity? So I have the link down there. Please check it out. It's super nice. And kind of this was the first kind of study which actually hooked me into trying to work on Gaussian processes for real applications. Most of the times when I work with Gaussian processes is actually to encode time-varying coefficients in linear regression. So in the usual linear regression, you have, let's say, y as a function of x, and you have a regression coefficient, let's call me beta, which is fixed. But in many applications, if you allow this actually vary smoothly over time, then you can grasp dynamics which are relevant for real case scenarios. So this is taken from a little case study that I wrote about this classical bikes data set where you want to model the number of bikes rented in a city as a function of many covariates and temperature. And if you fit a linear model, you have like a coefficient. Let's say how many degrees bikes do you expect to be rented if you increase the temperature degree by 1. But if you actually do like a time varying coefficient, you see that after 25 degrees or so, kind of the effect is actually lower than what you would get from a linear model. And actually, it's very interesting because I also compare it against having this type of model, this type of data fit into kind of XGBoost. And if you do kind of this partial dependency plot, you will get the same phenomena. But I just find having control on this kind of time varying coefficients, it's very nice. Where am I using it? And we are using it a lot. Well, we work on trying to kind of capture marketing efficiency over time, what is called kind of media mix models. And you would expect, in general, kind of the efficiency of certain channel, let's say the spend you put to have an effect on conversion, so to say, and you're interested in the cost per acquisition. Actually, I believe that the kind of base models where you have the kind of regression coefficients, which are not changing over time, are a good baseline. But if you want to kind of try to understand the dynamics over time, then this comes very handy. So I link also a blog post by the folks from PyMC Labs about this. And you can also vary the coefficients, but you can also vary the intercept. And by mixing these two, you can actually get models which fit the data pretty well. So I hope this conveys the message that what I'm going to talk today, even though it might look a little bit weird, it actually can be very helpful. So let me go into the section of Gaussian processes. So, oh no. Okay, let me try this. Classic. 1 second. Otherwise, it's going to be very weird. Oh no. Okay, so I hope you can compile LaTeX. This is the first time it happens. I apologize, and it's going to look very odd, so apologies for the recording as well. Okay, let's do that. Where is it? Okay, let's hope. Wait. Yeah! Okay. Thank you. All right. That was fantastic. All right. Thank you very much. You can still get the raw data because I provide that as well. So typical use case for a Gaussian process is that you have kind of the blue data, which is your training data, which looks weird. I know kind of where this is coming from. This is just a combination of sine and cosine, but actually in real practice, I don't know how this is generated. And I want to generate predictions kind of out of sample data, let's say on orange dots. And this is what we want to do. We can do this with kind of in different ways. We can use splines, we can use regressions, but we're going to see how this works for Gaussian processes. So the key ingredient, and I think this is why I like Gaussian processes a lot, and this is a very opinionated way of thinking, is that you can pass a lot of information through what is called the kernel. And you, as a modeler, are telling the model, let's say, kind of a measure of similarity between points. Because if you see this plot, I show in black the real data generation process, which is very smooth. But you could also tell the model, like, I'm expecting the Gaussian process to be not that smooth, or to be periodic, or to have certain properties. So this, you as a modeler, pass as a kernel. So this is not kind of a black magic that you're doing. So a kernel is a way of encoding similarity between points. And the most used kind of kernel is called the square exponential. And this kernel takes two elements and gives you a number. In this case, I'm just taking kind of this exponential of the difference and multiplying by kind of certain parameters. And these parameters are important. The A parameters is the amplitude, and it's going to control, let's say, how this shift on the noise, so to say. And the L is the length scale, which kind of, it's really actually the most important parameter because it's capturing how, let's say, how I'm measuring the closeness, so to say. So if L is very big as compared to the range of X, then if I change X prime a little bit, it's going to make very little difference. Whereas if L is small as compared to the range of these values, a little small change in X prime will actually change the value of the kernel quite a lot. And yeah, there are many other type of kernels, and if you have, what is nice is that these Gaussian processors can work as Lego bricks, because you can actually have many kernels, you can add them together and multiplying them, and kind of, it's a bit, it requires some practice, but if you can practice this intuition to actually capture the kind of what you expect as structural components of your data within these kernels. You, of course, don't know what A and L are, and you would like to infer them. This particular kernel has a property that, let's say, the dependency on X and X prime is through the difference, which means that, and this is important because it's going to come later, this is what is called a stationary kernel. So it really depends about the relative difference between these two. So if you plot this as a matrix, you can now evaluate this into, let's say, with respect to the whole training data set, and you have a matrix that is, the dimension is kind of the size of the training data set, and you see that kind of the kernel is concentrated along the diagonal, meaning that kind of points that are close together are going to be more similar. This is obvious, but this is what the kernel is looking. But notice something important is that this matrix actually scales with this kind of, it's as big as the training data set, which means if the training set is very big, this matrix is going to be quite big. So what's the whole point about a Gaussian process model? Well, you are going to assume that you can model this data as a multivariate normal. So this is kind of that generalization of a normal distribution where you have certain mean, which is not very important, but you care actually about the covariance of this matrix. So, which is kind of encoding kind of the similarity between these 2 points. So I denote X and Y, kind of the training data set, and by X star, the test set. I would like to know what Y star is. I don't know that. But kind of the way the Gaussian process works is that you are going to assume that the observations Y and kind of the latent Gaussian process F, because kind of you have this line that fits the data, but also you have the noise. So I'm assuming that the observations and this latent kind of fit on the test set come from a multi-normal distribution. And this matrix kind of bold K is actually splitted in between kind of the components. So it's evaluating the kernel matrix on kind of here the training set, here the training and the test, here the other way around, and here the test set. And this little sigma here is just to account for noise. And that's kind of your parameterization. And what you do, and you can actually do it by hand, is that this fit is just take this multi-normal distribution and condition on the training data, which is X and Y, and on the points of the test data where you want to generate predictions. So it turns out that if you do this game, you will also get a multivariate distribution, multi-normal distribution with certain mean and certain covariance. It's not important. What is important is that there are explicit formulas that you can compute by hand, but there's an interesting thing is that if you want to do it this way, you have to take the inverse of this kernel function, of this kernel matrix. So that means this is going to require a lot of computation, and you can do kind of Cholesky decomposition if you want, but there's no easy way of getting out of the fact that doing this for large kind of data sets is actually quite expensive. So the takeaway of this is that Gaussian processors are nice, but there's a price to pay, and it's through this kind of matrix inversion formula. But nevertheless, we can do it for this specific example, and in the Bayesian kind of paradigm, you want to understand also the values of L and A, and we can impose prior distributions, and this is a huge topic by itself about how to set priors on GPs, on Gaussian processes. But the intuition says that I will expect the length scale prior to be less than the amplitude, because kind of, if you see the plot before, kind of the range is between 0 and 1, and I have a lot of data points, so I want this distance to be kind of sensible with respect to this this distance, and the amplitude is between -1 and 2. I don't want to go into details, but this is kind of an ingredient to the Bayesian inference framework that you want to do. And you can do this very easily in PyMC. So I also do it in Numpyro, but kind of what you tell PyMC, if you are not familiar with the PyMC syntax, just think about like input-output. So you pass the data, you pass the priors of your kernel parameters and also about the noise. And there's a very convenient kind of min function, which we're going to assume is 0, and a covariance function on which you pass the kernel, and you pass the amplitude here, and your length scale, and to just feed that, and you are going to assume, okay, the likelihood, it's a normal likelihood. And this F that I have here is the latent Gaussian process. So 15 lines of codes, and you can fit this. Yeah, this is kind of how the model looks. The input are the priors, the output is the data. And within the Bayesian kind of framework, before kind of looking into the data, you can run what is called these prior predictions. I just mentioned that this is important if you're doing Bayesian modeling to assess whether the priors are good. And here I'm just kind of generating kind of feasible curves from the model without conditioning on the data. So this is on the first step. And we see that we're not being very restrictive and it's plausible. And then you feed your model, and what you get out of this feed is distribution of the kernel, amplitude and length scale, and the noise. And at the very end, PyMC gives you a very nice method on which you pass the test set, and then you condition. And this is doing this huge matrix thingy. So you actually don't need to know much about how this is happening. But if you feed this, this is going to take maybe 4 minutes, even though we have kind of 80 or 100 data points. So it's not great if you want to scale it to like 1,000 data points. But you get this nice fit on which the orange plot is kind of the likelihood, and the pink one is the latent Gaussian process. So within the range of definition, we capture this quite well. But out of the side of definition, actually the values that are kind of the predictions are kind of converting back to the mean, and also you get a lot of uncertainty because the Gaussian process says, like, I haven't seen that much data outside, so I want to be conservative and just go to the prior again. So this is just a little bit of caution. Let's say extrapolation with Gaussian processes is something that has to be done carefully. It can be done, but kind of depends on the data and the kernel. And then I can do this for time-varying coefficients. I can do all of these predictions on the presidential kind of popularity, and that's fine. But the key thing is that this doesn't scale well. And what we want to kind of present here is an alternative that has proven to be very successful. So this, I think, was published in 2020. There have been a lot of approaches, but this actually works quite well. So again, the problem is that if I want to do something with classical GPs, then I need to invert this matrix, and this is expensive. So the approach of the summary is the following. We want to find a way of approximating this kernel matrix with something which has a smaller rank. Because if we do so, and if the approximation is nice, then inverting something smaller, it's easier. So that's what we want to do. And here, kind of, I need to also have a disclaimer. I like kind of the ideas behind it, so because it connects various fields. So this is gonna sound a bit weird, but we'll try to make this more tangible. The whole point is that, and this is why we're talking about Hilbert spaces, is that there's a way of interpreting the kernel as kind of linking that to a certain differential operator. And differential operators on kind of functions form also kind of linear spaces, which are called Hilbert spaces, and you have a lot of spectral theory, like eigenvalues and eigenfunctions. So we're going to borrow a lot of kind of tooling from that world to try to solve this problem. So it's important not to get lost on the details, but to focus on the objective. But also, what I like about this is that it brings a lot of this spectral theory into the game. And at the very end of the game, we are going to essentially reduce fitting a Gaussian process to a linear regression. So hopefully that gets you excited. Well, not as excited as getting MathJax to work, but close. So this is a diagram. I'm gonna be very emphatic about the strategy and kind of try to go fast through the details. So we are starting here from the kernel. And what we're going to do is to associate what is called a spectral density, which is just a nice representation of a kernel. And then we're going to try to do kind of a Taylor expansion to see what we get. We get nothing unless we do something. And this other something is actually bring what is called the Laplace operator. And the Laplacian operator is being studied in physics, for example, quite a lot, where it appears on the wave equation, on the heat equation, so it's quite well studied, so we have a lot of tooling. And we're going to link this through the Fourier transform. And at the very end, we're going to arrive to an approximation formula. So this is kind of what you need to get in mind when you think about these APIs and feeding the data. I want to give you a glimpse on why this works, just because I think having a reference is useful. But at the end of the day, you can simply use the approximation formula. So what are we going to do? Going back to the diagram. So we're going to give a detour on eigenvalues and eigenvectors, because I think this is kind of the key component of this, and kind of it's often kind of overlooked, and I think it's a very strong theory. Then, as I mentioned, we're going to associate to each kernel what is called the spectral density, and we're going to run a polynomial expansion on this thing. And I haven't done anything unless I bring the Laplace operator, and I'm going to show or explain that if you take the Fourier transform of the Laplacian, you can actually plug it into this approximation. But you need to set certain boundary conditions to get all of this spectral theory working, and then we will do that in a second. And then you put this together just by kind of eyeballing the formula, and you get to a final linear regression. And this linear regression is what we have down there. So it's not really important about kind of what's happening. The thing is, I'm going to be able to fit a very simple linear model because I have like a usual beta coefficients here. I'm going to have these, what are the eigenfunctions of the Laplacian, which is something that it's easy to compute. So they're in the books, they're a function, I don't care about that. And what is most important is that they don't depend on the hyperparameters of the kernel, which means like A and L. So I just can store them somewhere and reuse them as I wish. And the only thing I need to do is to compute the spectral density, which is a function, again, that I know. There's nothing I need to do there, on the eigenvalues of the Laplacian, which is something that I know. So the story is that I do know how to do this very easily with a linear regression. So what is important for the detail is to count the factor and, let's say, understand why here's a root square and so on. But at the very end, it's a linear regression. So thinking about applications, what in PyMC run kind of the simple model in 4 minutes with 100 data points, it runs in milliseconds with the approximation. And there's already kind of a nice API to do this. So I guess the main component here is about eigenvalues and eigenvectors. So you have a square matrix. Remember that an let's say eigenvector and eigenvalue pair satisfy this property, meaning if I take a matrix, multiply it with a vector, I get a scalar lambda times v. I want v not to be 0, so that it's not trivial. And I say that the spectrum of this matrix is the set of eigenvalues and eigenvectors. And probably you've done this quite a lot in school, but it's still very, very useful. So if you want to see an example, I have this 2 by 2 matrix, and one can show that the eigenvalues are 3 and -1, with eigenvectors 1, 1, and -1, 1. And one can add this kind of funky factor so that kind of the inner product between these two is 0 and the norm is 1. And there's kind of an easy way of doing this. I also provide resources if you are a little bit rusty, but this is kind of the gist. But kind of eigenvalues and eigenvectors by themselves might not seem that interesting. What I think is one of the most interesting theorems or result in linear algebra is what is called the spectral theorem. And it just simply says that if you do that procedure and you use these eigenvectors as a change of basis, so trying to change the coordinates, your operator or your matrix, which in this, if it's symmetric, is always going to become diagonal, which means you can just work with diagonal matrices, which are just much nicer. So this is a very interesting result. I think, and it can generalize to a much wider kind of scope. So I probably don't want to go into details, but I provide this example. So you can use JAX or NumPy, and you can actually test that what I'm telling you is true, which means if I give you a matrix minus 1, 2, 2, 1, you can compute the eigenvalues, and the JAX gives you this in a normalized way, which is 1 over square root of minus 2, of 2. And if you do the change of basis kind of game, you actually get a diagonal matrix, which is super nice. And one interesting thing here is that you can actually write your operator as a sum of the eigenvalues times kind of taking the inner product with V and multiplying, which will, if you apply this to a vector, will give you a scalar, and then multiply it with the vector again. And this is kind of, it's very, very useful for what we're going to do, because instead of working with matrices, we can just work with these sums. And these sums are actually quite convenient. So this is what is called a spectral projection, because it's indeed a projection. If you do this twice for these operators, you'll get the same thing. And in the notebook, I show you some examples where I see if I kind of do this, this actually works for all vectors. So, but the most important thing about this is that if you have such a representation of an operator A, if you take a function of this matrix, let's say take a square or take an exponential, this is actually as simple as taking the function on the eigenvalues here. So remember that multiplying a matrix is not, it's like you need to do this game with the rows and columns, but here I'm telling you just write the matrix as this kind of spectral decomposition, so to say, and if you want to apply any function, then the only thing you need to do is apply the function to the eigenvector. So easy examples, if you have the identity function, you recover the operator A. If you put f set equals to 1, then this is just going to be the identity matrix. And you can take the square just by taking kind of squares of the eigenvalues. And you can take exponentials of matrices just by taking the exponentials of these eigenvalues. So this is what we're going to do, and this is why the spectral theorem is so useful, is because it allows you to take any type of functions on matrices just by evaluating this. So you can do this by pen and paper. You don't need to mess up with any matrix. And this is just very convenient. So this was kind of a small detour, but what we want to do is actually go to our kind of kernel. So one thing that that one can show is that if I have a stationary kernel, which means it depends on x and x prime as a difference, then you can always write it kind of as an integral representation. This is the ugliest slide that I have, so apologies for that. But think about it as a Fourier transform. It just happens to work. And there are very kind of clever mathematicians that actually compute this. So given a kernel, you can go to Rasmussen's book and just look for the spectral density, and they say, OK, I have a formula. And they look like this. So they depend, of course, on the parameters of your kernel. So this is for the square exponential. And this depends on a auxiliary variable omega. And this goes as a kind of Gauss bell shape in omega. But what is important is that you can just write these formulas in NumPy, and I provide such a code. So it's very simple. So again, think about this as a Fourier transform, and where you don't need to think because these quantities are given. Yeah, and here I show how the spectral densities for the square exponential look. They have this feature that they always decay at infinity. So what we can do actually is assume that there's going to be a Taylor expansion of these spectral densities. And you can just assume this with certain parameters A, which you don't know. And you say, OK, if I kind of were able to read this from somewhere, then I could maybe truncate this series and do something clever. But at this point, this is where other side of the story comes in, and it's the Laplacian. So the nice thing, and I guess the key idea of the approach, is that the expansion they do on the square of omega. And I'm going to give you a reason for that the paper doesn't give, because they go really fast, and it has to do with the Laplace operator. So in another world, you have the Laplacian, which physicists have studied quite a lot, and this is this operator that takes the second derivative of a function. And it has a lot of properties that people like, but one property that we're going to use is that if you take the Fourier transform of this operator, it gives you a polynomial of order 2. So the whole idea is, okay, I have this in my expansion. This is actually can be interpreted as the Fourier transform of the Laplacian. So let's try to plug this in by brute force and see what happens. So you can actually do that. So you just can consider the operator on which you replace the omega square by the Laplacian and see what can happen, because that's another way of interpreting this omega square. But here you haven't gotten anything, because if you have studied kind of the differential operators, you know it's important to define a domain of definition or boundary conditions. So one very common boundary condition is to assume that the functions in the domain of this operator vanish in a boundary of certain domain. So you can put your data into certain box and assume that all of the functions are going to vanish here. And if you consider the Hilbert space, so that's why the name of the approach, of all of the functions that are square integrable and satisfy the boundary condition that they vanish on the boundary, then this is actually a symmetric operator, self-adjoint. And what you gain with this is that you have the spectral theory. You can do exactly what I said for matrices, meaning the spectral theorem, taking the functional calculus, and taking powers of the operator just by taking the eigenfunctions of the Laplacian. So you get a lot of kind of spectral theory, and we are very happy because we know how to actually take powers of this polynomial. That's the motivation of kind of the bottom formula. We want to do this in a clever way. And we know if we have a spectral decomposition, we can do it just very easily by taking powers of the eigenvalues. So this operator on the set of functions that vanish on the boundary actually has a discrete spectrum which grows to infinity, and I have eigenfunctions which actually I can compute. And why I can compute? Just because you know how to solve this differential equation, which is just take which function, if you take the second derivative, would give you minus that function and vanish at the boundary. Well, this is the sine functions. So I guess if you have taken any physics course or basic math or kind of differential equations, you know that this is kind of the first exercise that you can do. And so we all know how to do that. You can wrap this into a little function and just move forward. So if you want to see the plots, these are just sine and cosines, just sines moving around the boundary, and you usually take the box, let's say this minus LL, to be sufficiently big so that you have the training data here, because that's going to be where you want to do kind of extrapolation. And kind of the final step is actually noticing that if I want to take powers of the Laplacian, the only thing I need to do is take powers of kind of the spectral decomposition. And this is what I've written in red, if you can see. So this is just the last step. It's about kind of identifying the Taylor expansion of the spectral density and computing this in terms of the eigenfunctions of the Laplacian. But notice that you don't need to do anything, because if you want to take powers of this huge thing, you just need to take powers of the little eigenvalue. This is what you're winning. You don't need to compute anything if you have such spectral representation. And through these identifications, you realize that in order to kind of identify this coefficient, kind of the parameters are actually evaluating the spectral density on the eigenvalues of the Laplacian. This is just by eyeballing it. So if you look into the papers, this takes kind of less than 1 page, but they don't explain the why. So kind of my take-home message is that everything has to do with the Fourier transform. This is kind of the link. And at the very end, you get this final representation, which kind of, if you translate it into the world of the Gaussian processes, it just says that you can truncate, you just compute the eigenvalues of the Laplacian, compute the eigenfunctions, and compute these things that you can actually do very easily because you can pre-compute it. They don't depend on the Gaussian process, this blue one, and this one as formulas you can get in the book. And we get to the final linear regression. So at the very end, we get to this very easy formula, which again, you don't need to know it or the derivation, but I think is helpful when you're working with these models. And for one-dimensional case, I do this in the notebook. I do this explicitly and actually show that what I do in Numpyro by hand actually coincides to what PyMC is doing behind the scene. So again, take home is this. I can share a link. I will share the link for the papers, but it's just another ways of seeing that how all of this spectral theory can help us solve a very concrete problem. So back to the example, these are now priors that I can get, but instead of having a GP, I have this linear regression. So this looks quite reasonable. Everything I told you about this weird theory can be written in less than 30 lines of codes, because these are just kind of sine, cosine, exponential, and it's provided there. So this is something that is just kind of a linear regression, so you can just use these helper functions for your applications. You don't need to actually rethink it yourself. I want to skip this because I want to show you that the results that you get is the traces on the parameters, which are the kernel amplitude, the length scale, and the noise. These are actually the same, like almost the same as what you get with the Gaussian processes, kind of vanilla implementation, but you also have all of this beta coefficient, which is kind of the number of terms in the expansion, which are just kind of linear terms. And this fits very, very fast. And this is the result that we get, which is very similar to what we got before. It's pretty much the same. PyMC actually gives you a very nice way of doing it, and the only thing you need to change is GP to SGP, or like HSGP. And it provides kind of a very simple API, so going from vanilla Gaussian process to Hilbert Space approximations, you just need to change one line of code. But now you have certain control of the number of functions to use. In this case, I'm using 20, and the L, which is kind of the size of the box. So hopefully, if you use PyMC, you already know that this L has to do with the Laplacian, where I'm doing the approximation, and this M has to do with the eigenvalues, eigenfunctions that I take. And I can use the conditional method. I have to do the same thing, and I get exactly the same results. So kind of, you can take this as for granted. PyMC gives you a way of actually getting the spectral density yourself and the eigenvalues of the Laplacian, eigenfunction of the Laplacian. If you want to do something funky, it's also supported. So please check it out. Again, I do both implementations in the notebook. So kind of, I can do out of sample predictions in a similar way. Yeah, and that's what I wanted to talk about. And about references, as I mentioned, kind of we have the classical papers here on the Gaussian processes, but this little notebook is actually an open PR where we are working on having even more practical examples on how you can use hierarchical models on these Hilbert space approximations and do this on, for example, 2 dimensions, which Hilbert spaces are also quite useful. Yeah, so I'm sharing this with you. And yeah, thank you very much.
Thank you, Juan, for your introduction to HSGP. We have some questions on Slido. The first one is, how does HSGP compare to other GP approximations, especially to stochastic GPs fitted with variational inference?
So I don't know the details. I haven't studied that much those. What I do see kind of a difference from what I heard is that here you can use full MCMC, whereas in variational inference, you need to kind of specify kind of a family of the posterior distribution. So I guess what we gain here is that you don't need to impose that, and it could work well if you have kind of bimodal distributions. But I don't have any concrete answer for that.
Are your choice of boundary conditions causing bias, especially for large length scales?
So kind of what it's recommended, let's say this is kind of the theory, but what it's recommended in practice is that you center the data. So if you have your data like this, you actually move it in such a way that the mean is 0, and you take L big enough. And this kind of, the choice of L, it's a little bit tricky, because if it's too small, it won't be able to extrapolate that well, but if it's too big, then these things are going to vary quite slow. So there's a paper here, which is this one, which I strongly encourage to read, which is Practical Hilbert Space Approximation. And this is where the authors go into the empirical studies about how to select this. And this is more kind of trial and error and kind of rule of thumb tricks.
So a short HSGP is much faster than vanilla GP. Any drawbacks of HSGP?
So it's definitely much faster, and I don't think you lose a lot. Of course, there are things that don't work. For example, if you go to very high dimensions, then it doesn't work that well. So for dimension 1 and 2, which is the cases where I've used this a lot, it works pretty well, but it also has the limitation of the input dimension.
For which kernels does HSGP work?
So it works for most of what you can think, so square exponential, all of the Martin families, which are the ones which are non-smooth, and you have all the spectral densities, so you can just use that from the books. Periodic, it's a little bit weird because it doesn't work exactly like this, but the authors of this paper actually make it work. So I say in practice, all of them that you will use in a typical use case. For the periodic ones, you can, but yeah, no, but for example, the linear then is faster to fit. So yeah, I think the linear it won't, but kind of the ones that you usually use, yeah. But yeah, I agree that some of them won't.
What again is the speed up of HSGP in your example?
Sorry?
What again is the speed up of HSGP in your example?
So I didn't benchmark quite thoroughly, but at least in PyMC, it went from 4 to 5 minutes to milliseconds. So, and in practice, I never work with vanilla GPs.
If the main advantage of HSGP is speed, can we apply it to the deep Gaussian process?
I'm not an expert on that, but I would, if you are using vanilla Gaussian processes, I wouldn't imagine why you shouldn't or you couldn't do this, but I haven't tried myself.
Last question. What about high-dimensional data?
Yeah, that's what I mentioned, that dimension 1 or 2 works fine. Higher dimension, it gets more complex because now, and this is why it's important to know about the theory, you'll have the eigenfunction of the Laplacian on all of the dimensions, and then you need products of them. So this will increase quite a lot with the dimensions. But in most cases that I've worked, which is dimension 1 and 2 for geospatial data, it works quite well.
Thank you again for answering the question.
All right.
Thank you for your talk.
Thank
you.